In this video, we're going to be continuing our discussion of electronics and circuits by starting to discuss how we can analyze a circuit of passive elements like resistors, conductors, or capacitors and inductors. Um, and the main way that we analyze this is through Kirchhoff's laws. So there's two different laws that we use. So the one is Kirchhoff's current law, which we abbreviate as KCL, and the other one is Kirchhoff's voltage law, which is KVL. And so we'll start with KCL, so Kirchhoff's current law. And Kirchhoff's current law is that the sum of currents entering and leaving a node, sorry, that should be two words there, a node, is 0. And so if we have some sort of circuit, maybe we've got some sort of voltage source, and then we have a resistor, and then if we have a branch with like maybe a capacitor here and an inductor there, maybe we'll go ahead and close that circuit and go to ground. Then the sum, if we have a node where we've got this branching of wires, then the sum of the currents entering that node is equal to the sum of the currents leaving that node, or they sum to 0. So if I write some sort of current going through a resistor here, and some sort of current going through the capacitor there, and some sort of current going through the inductor there, the way I've drawn it is that the currents entering the node currents entering, that's just IR, that resistor going through it. And the currents leaving is going to be the sum of IC plus IL. And that means that IR equals IC plus IL. And so this is a fundamental law, and we have relationships that we can start to plug in that allow us to analyze this circuit. And so IR is going to be, if I start labeling things here, I'll label this node A, B, and ground over here I'll call C. You can see that the one side of this capacitor is connected to the same side of this that side of the inductor. That's all one node. So IR is VA minus VB over R, and we know that IC is equal to the derivative of the voltage going through the current, and so that equals, I'll go ahead and write it the way we wrote it in the last video. So it's C times some dV dt, which is going to be the same as C times VB dot minus VC dot. And then IL is an integral. It's going to be equal to 1 over L times the integral of, again, you start where the current starts and subtract where the current ends. VB minus Vc. And there's some taus in there, which I'm leaving out, but it's the integral of the voltage. So we'll go ahead and say we'll plug all of those into our equation. Va minus Vb over R is equal to C times Vb dot minus Vc dot plus 1 over L times the integral of Vb minus Vc. And one trick that we can do when we see this integral is we don't really want to deal with it. Integrals are not so good. Well, they're fine. They're good. They're useful, but they're harder to analyze. And so if we just take the derivative of both sides, we can get rid of that integral. So if we take the derivative of VA minus VB over R, we'll just have VA dot minus VB dot over R equals C times VB double dot minus VC double dot plus 1 over L times VB minus VC. And this can be rearranged into a second order linear differential equation, which we've been dealing with so far up to this point. I'll briefly touch on Kirchhoff's voltage law, which uses a similar process, which is that the sum of the voltages or the voltage changes around a loop is 0. So if we draw the same circuit, some resistor, some inductor, and some capacitor, and we'll go ahead and connect all of that and connect it to ground. There's some voltage here, I'll call it VR, which is equal to VA minus VB. I'll label my nodes again, A, B, and C. And then there's some VC and some VL. You can see just by looking at the circuit that we have two loops that form. One is right here, and another one is right here. So if we take this loop, we'll do the one on the left first. We'll say this is Vn, some voltage source. If we start from the bottom right here, and we can use a positive voltage source, but then as we go through this direction, we're going to subtract VR and then subtract VL. That equals 0. And so an analogy of the pressure, if we if we go if this voltage source makes us go up in pressure, the resistor makes us go down, the inductor makes us go down again, and we start back where we started, the voltage better be the same, or the pressure or the voltage better be the same again. And that's what that thing says. Same on this other side, we can say that a minus VL minus VC must equal 0. And just how we started with the current laws and ended up with voltage relationships, if we start with the voltage law, we'll look at the current relationships. We'll start plugging in our current relationships to get equations of motion for this system. We'll stop that video there.